There are two very important bases for computer applications, and a third that has some importance. The two that are real important are binary and hexadecimal. There's also octal, and we're not going to really talk that much about octal. Your text does talk about it, and I believe you can read about it, and if you understand the binary and hexadecimal, then I do expect that you'll be able to do the octal. Binary is base 2. So if we have the decimal number 114 and want to put that into base 2, first we want to write our powers of 2. 2 to the 0 equals 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64. 2 to the 7th would be 128, which would be bigger than the 114, so we're not going to bother with that. And then we simply work backwards. We use 1, 64, leaving to get to the 114, well, we need 50 more. Now if we need 50, then we're going to use 132. Of the 50 that we need, that leaves 18. To get the 18, well, we'd better use a 16, which leaves 2. To get the 2, we can't use a 4, an 8. We can't use a 4, so we don't use either of those. We do need to use a 2. Leaving us nothing, so we're not going to use any 1s. The number that we get, therefore, is 1 times 2 to the 6th plus 1 times 2 to the 5th plus 1 times 2 to the 4th plus 0 times 2 to the 3rd, 0 times 2 to the 2nd, 1 times 2 to the 1st, and 0 times 2 to the 0. So we can say that 114 equals 1 times 2 to the 6th plus 1 times 2 to the 5th plus 1 times 2 to the 4th plus no 2 to the 3rds and no 2 to the 2nds and a 2 to the 1st and no 2 to the 0s. Let's zoom in just a little bit so we can get a good close look at that. And of course then that's going to be written as 1, 1, 1, 0, 0, 1, 0, base 2. Now the hexadecimal system is a base 16. Hexa meaning 6, decimal meaning 10, 6 and 10 makes 16. In the hexadecimal system, the numbers would go 0, 1, 2, 3, all the way up to 15. Now the problem is we can't use two-digit numbers to represent things in a place value system. We can't represent a place by a two-digit number. So we'll see what happens. The hexadecimal numbers then go up to 4, 5, 6, 7, 8, and 9. And the corresponding binary numbers, the binary for 1 is 1, the binary for 2 is 0, 0, 1, 0. Binary for 3 would be 0, 0, 1, 1. This representing 1 times 2 to the 1st plus 1 times 2 to the 0, which is 2 plus 1. And then 4 would be 0, 1, 0, 0, representing no 2 to the 0, no 2 to the 1, a 2 to the 2nd, 2 to the 2nd being 4, and nothing else. Then if we want 5, we're going to have to add 1 to this. We could write that as 0, 1, 0, 1, 2 to the 4th plus 2 to the 0. 6 would be 0, 1. We're going to have to add 2 to the 4. 2 is represented with a 1, 0 over here, so we have that. And if we continue, it goes like this, using the second, first, and 0th powers of 2 to make up 7. Then 8 is going to require the third power of 2. 9, the third power of 2 plus 1. And then where do we go? We got to get up to base 16. Well, let's continue the table over here. We're going to use, instead of 10, we can only use a single symbol. We're going to use A, then B for 11, and C for 12, D for 13, E for 14, and F for 15. Okay, so this A through F stands for the numbers 10 through 15. Now the binary of A, or 10, would include a third power of 2 plus a second power of 2. Whoops. I'm sorry, third power of 2 plus a first power of 2. I just said it wrong, and then managed to believe myself there for a minute. Okay. 11 is going to require the first power, the third power plus the first power plus the 0th power. That is an 8, a 2, and a 1. C, which stands for 12, will require an 8 and a 4 and nothing else. D will require an 8 and a 4 and a 1. E requires an 8 and a 4 and a 2. And F requires an 8, a 4, a 2, and a 1. Okay. So that the binary representations of the hexadecimal numbers are here. Decimal representations are the same as the hex here. Over here, the decimal representation would be 10, 11, 12, 13, 14, and 15. Let's represent the number 463 in hexadecimal form. Okay, in hexadecimal form now, the first digit represents, remember we're talking powers of 16. 16 to the 0 is 1. 16 to the 1 would be 16. 16 squared would be 256. 16 cubed is 4096. We're not going to need this. In order to make up 463, we're going to use one times 16 squared, which gives us 256, leaving us 463 minus 256 is 107. Now we need another 107 to get the 463. To get 107, we can use 6 16s. That's 96. Out of the 107 that we need, that leaves 11. And then 16 to the 0, we're going to need 11 times 16 to the 0, which gives us the 11, but we represent instead of 11, we're going to have to use B times 16 to the 0, because again we can't use a two-digit number in a place value system. So that 463 hex, or 463 binary, equals 1, 6, and instead of 11 we have to write B. That's 16B hex. If we wanted to write this number in binary, having written it in hexadecimal, what would that be in binary? Well, you should actually go ahead and try to work this out in binary and then see why it does what it does. Okay, the 1 in the hex means 1 times 16 squared. Actually, let's do it the other way. Let's start with the B in hex. The B, the last digit in hex, stands for, of course, the decimal number 11, but it stands for the binary number 1011. So we can write this as 1011, standing for the B in hex. 6 in hexadecimal, or 6 hexadecimal, the number 6 in hexadecimal means, of course, 6 times 16. The 6 can be written in binary form as 0110. So if we just convert the digit of the hexadecimal to binary form, we're going to build up the binary form of the original number. Now the 1 in hexadecimal means just 0001 in binary. So that our final number is 0001, and I'm going to leave a little space here, 01101011, binary. The conversion of hex to binary is such that if you just convert each hexadecimal digit to its binary counterpart, using all 4 digits of the binary counterpart, you get the binary number. Now, of course, the 3 zeros at the very beginning, the 3 leading zeros, could be let off, so we could say, could be left off, and we could say that this is the binary number. We don't need these, but we do need the intermediate zeros, this one, and so forth. We can't just leave a leading 0 off of an intermediate number here. Leading 0 off of the very first number to the left, yeah, we can do that. So there's a conversion of hexadecimal to binary, and you can read more explanation about that. If you actually work out the binary equivalent of 463 without going through the hexadecimal, you'll see that this does work, and you'll get some insight as to why it works.